So, now we will move on to the shielding gases, shall we, right. So, we looked at the heat transfer characteristic, right, the conduction, convection, radiation. So, you should recall all the time. So, when the moment you say the selection of gases, whatever we learnt in the heat transfer, it is extremely important to relate that over the selection of shielding gas. Okay. So, the function of gas in the welding process, primary function is to strike an arc, is not it. So, the gas, the shielding gas what you use, the main function you use it to strike an arc, and then you can use the gas to protect the weld pool. Okay. The shielding gas which you use is not only used for arc is a primary function, but secondary function again it is not only to protect the weld pool. The shielding gas influences the various aspect of welding. Okay. So, it of course, it protects the atmosphere, but it will also change the weld bead geometry. It can also change the microstructure. It can also change the fluid flow. Okay. So, all these things should be taken into consideration when you are choosing a shielding gas. Okay. So, the primary function as I written down here, to sustain a low voltage arc, that is the primary function, and then protect it from the atmosphere. But secondary the functions, the arc can also influence the bead geometry and mechanical property. So, one classical example is use of oxygen in a low carbon, medium carbon steel for welding. So, we add some amount of oxygen with argon, for example, to induce oxide inclusions. Okay. So, the moment you induce oxide inclusions, the oxide inclusions where the acicular ferrite is nucleating. Okay. So, acicular ferrite are nucleated at the oxide inclusions, sorry, metallurgy, pardon me. Okay. So, once you have the oxide inclusions, so you can nucleate acicular ferrite, and acicular ferrite, if you have in microstructure, the toughness increases significantly. Okay. So, that is one example I want to give. Or you can also use a high conductivity gases, for example, hydrogen or helium, to spread the weld pool. Okay. So, by spreading, so you can also increase the area you weld. So, you can do a wider bead geometry weld. So, based on your need, by looking at the characteristic of the shielding gas, so we can choose which shielding gas you want to use for welding, right. So, we look at one by one, looking at the characteristics. So, by far argon is very widely used for GTAW. GTAW is most of the cases is done using argon, right, and sometimes we mix argon with a diatomic gas, for example, argon plus CO2. Okay. Again, the CO2 can influence the heat transfer characteristic of an arc, because CO2 is a diatomic gas, right. So, obviously, the heat transfer can be very effective. You start look at because of diatomic dissociation and then de-dissociation, your arc heat can be distributed much more uniformly than if you use argon, right. Similarly, if you use gases with high thermal conductivity, same phenomena can also be happening. For example, if you use hydrogen or helium, helium is highly convective gases. What do you mean convective? The buoyancy flow is very high if you use helium or hydrogen, is not it. So, the heat can be transferred very effectively. So, you will have making a very wider wells, because the heat is spread, right. It is clear. So, we look at one by one all the gases what we commonly use, and then what are the characteristics, and then to understand what gas you want to use for your given application. So, you need to look at the physical characteristics of the gas plus the physics of arc, right. It is clear. So, generally diatomic gases with gas thermal conductivity result in wider bead because of the effective heat transfer. Diatomic gases, the de-dissociation can transfer the heat. Similarly, the convective gases, high thermal conductivity gases can also transfer it by effective buoyancy flow. And during this process, if the arc, the temperature is widens, you also increase the voltage in most of the cases, because the flow is diverted, it is not going and it is diverted. So, obviously you end up increasing the voltage as well, system voltage. Okay, it's clear? Okay, good. We will see one by one. So, this is a classical example of the arc pressure measured over the distance, the diameter of the arc, by using argon and helium and argon. You see the difference already? So, helium is highly convective gas, is not it? The heat transfer is very effective by convection due to the buoyancy. When helium or even hydrogen, and because of that, if you use only argon, so you will have the enormous amount of heat concentrating at the arc core. The argon does not, it is a monatomic gas, it does not dissociate because it is an already atomic gas. So, the heat is not transferred effectively from the center of the arc to the circumference, right. Whereas, if you mix, say for example, helium and 25% argon, the helium would transfer the heat effectively from the center of the arc to the arc envelope, and during this process the pressure or in temperature would decrease significantly at the center because it is spreading out, it is transferring. So, now if you use the same welding parameter, you just change the shielding gas, which would give deeper penetration. So, in this case argon would give much deeper penetration because heat is concentrated, is not it? Suppose if you use the second mixture, your well bead will be something like this, is not it? So, now you can clearly see just by changing the shielding gas, you would change the well geometry, right. So, if you use argon, so heat is concentrating at the core of the arc, so it will lead to a deeper penetration, very narrow weld. And change it to helium, which is convective gas, or you add argon CO2, carbon dioxide, you will see the effect already. Okay. So, carbon dioxide, which is also effective in heat transfer because of de-dissociation. Okay. And the helium and hydrogen is also very effective because of effective convective flow. In both ways, the heat can be distributed from the core to the envelope periphery. Yes, it is clear, and it is real, and we have done experiments to verify that. So, in this case, so we use argon as a main gas and we added various gases along this argon. Okay, so, in the first case we will start from here, and this is argon only 2.5% CO2, it is close to pure form. You see that the very deep, even the well pool is collapsed because of superheating, it sagged, very narrow weld, is not it. So, if we start increasing the carbon dioxide concentration, you already see the penetration is decreasing and then it is becoming wider, is not it. So, again increasing the carbon dioxide, it is even wider, the penetration decreases significantly. Okay. And from here to here we added the oxygen O2, it even increases the well bead width and penetration decreases. Okay. This is due to the phenomena I already explained because of the change in the heat transfer of the arc, right. So, this is what happens when you have an argon or argon CO2. So, the arc core is very narrow in argon case, because the heat is not transferred. So, there is no convective heat transfer, there is no dedissociation, the conductive heat transfer by dedissociation. So, you will concentrate heat at the core the maximum when you use a pure argon, right. So, you will have very narrow core and leading to the deeper penetration in argon. So, you mix with CO2, okay, the R core expands because the heat is now distributed by the dedissociation. So, the Kd term would influence the temperature distribution from core to the outer periphery, and during this process so you will also distribute the heat leading to the wider bead and then shallow penetration. Same would happen if you replace this with helium or even hydrogen, then instead of Kd you will have a much more effective buoyancy flow. Okay. Yes, because they are all very effective the convective gases, which have, that is why we always say the helium and hydrogen, they have very high thermal conductivity, okay, because of the convective heat transfer, effective convective heat transfer, right. It is clear the effect of shielding gas. So, you can now immediately think about it. Now, you want to reduce the penetration, you see the weld is penetrating very high. So, with argon, okay, let us add 5% CO2. Okay, so, obviously, the penetration will decrease, weld bead width will be increasing. You should also have significant width, otherwise the load will be concentrating on a very narrow region. So, the weld width would also be the aspect ratio of the weld, the width to the depth ratio, it is also very important, right. So, that is how we change the shielding gas in such a way that we change the weld bead geometry. So, not only that, the shielding gases will also influence the microstructure generation. Okay. For example, as I explained, the oxygen will form oxide inclusion, and that is beneficial to nucleate acicular ferrite, right. So, we will look at the one by one all the characteristic of the gases, then we will stop. Okay. The first argon. So, argon is widely used for GTAW, is totally inert and denser than air, it is very important. So, when you use argon shielding gas, it displaces air. Okay. So, the air is displaced effectively when argon is purged, because it is denser than air. So, it has a low ionization compared to helium. Okay. Okay. So, therefore, the ignition is easy compared to helium. So, that is why when you are using the argon in GTAW, the arc ignition facilitated by the electric breakdown or high frequency ignition, because if you use helium, the ionization energy is high. So, obviously, VB which we saw, it has to be even higher. Okay. In high frequency ignition, you need to increase the frequency even higher than what you use for argon. So, the argon is preferred for GTAW for this very same purpose, because the ignition is easy, right. Okay. Sometimes we add hydrogen mainly for stainless steels, because stainless steels, so we need to spread, I need to weld it with the wider heat, the arc envelope. So, if you use argon, so you are always concentrating onto very narrow region. So, we add hydrogen 5%, so that the heat is distributed, so you make wider bead, right. It is clear. Can you use hydrogen mixing for low carbon steels or steels, ferritic steels? Yeah, so we can use. So, if you use hydrogen for welding low carbon steel, then you will be fired, because the weld is going to crack by hydrogen embrittlement. Okay. So, pure argon is generally not used for GMAW. Okay. So, again the heat is highly concentrating at the arc core, the melting characteristic of the filler cannot be ensured properly. Okay. So, GMAW if you use argon, generally you need to melt the droplet and then transfer it. The transfer characteristics is significantly affected by the arc core, the shape of the arc core. So, we will see when you are looking GMAW why it is very important. So, generally we do not use argon for GMAW, but nowadays people use it because the control over the wire feed rate. Okay. So, in those days when the wire feed rate is not synchronized with the power source and the waveform characteristics, the argon was not used for GMAW. Okay. So, now we can control it, but mostly we do not prefer to use argon. So, second is helium. So, helium is very light, it is lighter than air. Now, we already have a problem. So, if you want to use helium as a shielding gas, flow rate must be significant to displace the air, is not it? So, argon it is denser than air, even if you send is reasonably low flow rate, it would still displace the air. But helium you need to have enough pressure to push the air, so that you fill the medium with helium. It is lighter than air, it is one of the two gases which can escape from Earth's atmosphere. Which is the other one? Hydrogen, obviously. So, helium if you send via balloon, it would escape. Okay. So, I always feel someone uses helium for filling balloons and fly it, because it will escape. So, we will run out of helium for welding, right. So, I would always discourage my children using helium balloons. No, I need it for welding. So, if you all of us send helium balloons to atmosphere, it will go away to space. Okay. So, then we run out of helium. So, luckily we can produce helium in Earth itself. Okay. So, because the nuclear reactors, the final product is helium. Okay. But that is very costly helium. So, most of the helium comes from the volcanoes. Okay. The Earth's crust has helium. Okay. So, we produce helium. Obviously, we also need a very high arc voltage. Why? Because helium has a very high ionization potential, right. Otherwise, we cannot sustain the arc ignition, is not it? So, it needs high arc voltage than argon, and that would lead to obviously high heat generation. So, the helium arc would always be hotter than argon arc, because when the helium is ionized, it is ionized with very high ionization energy, right. So, then the energy is released. Obviously, the electrons which are coming out of the ionization process will also have a high energy, and obviously high energy electrons are collide, you also transfer the energy much higher than when you have when low energy electrons are coming out. So, this collision obviously lead to high temperatures. So, arc temperature will always be higher than, for example, if you use argon. Okay. All these put together will increase the heat input, right, and leading to a larger fission zone. And there is one advantage, because you can also do high speed welding. So, you can also, instead of doing it slowly, you already have a large amount of heat. That means that you can do it slightly faster. So, the welding speed can be increased compared to argon. So, the cost you spend to buy helium bottle is compensated by welding in increased speed, right. But it is only production environment. It is also widely used for high conductivity materials, because the heat, the energy, the arc energy what is there, it is high. Okay. The heat is generated in a high amount compared to the argon. So, in high conductive materials, heat is dissipated so quickly. So, you need to supply more heat so that you can melt, is not it. So, for example, welding copper, helium is very widely used because it is a highly conductive material. So, you need to supply more heat to melt the interface, right. It is clear. Helium? Good. So then third commonly used gas is carbon dioxide. Okay, the carbon dioxide is a very active gas, right? So it also dissociates into oxygen and carbon monoxide, isn't it? So this dissociation lead to reduction in R core temperature, the same example I showed you. So dissociation can lead to de-dissociation elsewhere. During this process, the heat can be transferred. So due to that, the R core temperature decreases because you are spreading the heat. It is not concentrated at the core, so the temperature is spread. And this dissociation process also generate oxygen atom. So oxygen can react with the molten metal. Unfortunately, it can react with aluminum, for example, silicon. So when you are using CO2 and if a steel contains aluminum, the aluminum will be lost. The aluminum pickup is very low when you are using CO2 welding, because the aluminum would all go away as aluminum oxide slag. Okay. So generally, because of these phenomena, the arc stability decreases because the arc core is not narrow, so it is spread, and you also create the more ions and decrease the ion concentration due to the dissociation and de-dissociation process respectively. So then the arc stability will not be there, right, compared to monatomic gases when you are using CO2. So but the voltage will be higher, again the same process, because you are spreading like in the conductive gases. So voltage will increase, therefore heat input will also increase, okay, but the stability will go down significantly. Okay. So using conductive heat transfer to increase the arc temperature, the widen the arc temperature will be better than using CO2. Okay, that will give you much more stable arc. But in this case, the stability will go down. So it's low cost carbon dioxide. Okay, so argon plus CO2 mixtures are very common, right, to spread the heat in the arc, so that we can reduce the penetration and we can widen the well bead significantly. Yes, it's clear. We look at two more gases and then we stop. Oxygen. So oxygen is always used in mixture. You can't do a welding with pure oxygen for obvious reasons. So you will have explosion, right. So it is used widely to mix either argon, mostly argon. Okay. So it is known to improve the arc stability, right, but again you have a diatomic oxygen O2 would lead to de-dissociation and spreading, and it will also influence the surface tension. Okay. So that is very significant effect you would see in bell geometry. We will see in subsequent classes how the surface tension of the molten metal would change the bead geometry. When the oxygen dissolves, it is known to change the surface tension. So then your fluid flow behavior will change. You may even change from the outward flow into inward flow by changing the surface tension as a function of temperature. Okay. So we will see how. So this is another function of shielding gas. Okay. Microstructure. Oxygen would influence the inclusion formation. It will also influence the surface tension, will change the geometry of the bead as well. Okay. So you would end up oxidizing the highly oxidizing alloying elements. You have silicon, for example, aluminum. So your well bead would be depleted of these elements. Okay. So when you use an MEAW electrode, last week one of my students he came to me, we wanted to add aluminum in the electrode, we end up getting nothing. The well bead did not contain any aluminum. So in a metal arc welding, it is done without shielding gas, because the CO2 we generate by dissociating the flux. Okay. So you end up making oxygen and carbon monoxide, and oxygen what is generated by the dissociation would eat away all the aluminum, and the aluminum oxide will glow as a slag during welding. Okay. And this process you also generate carbon, and the carbon would also lead to, the carbon would diffuse to the well metal, and the carbon concentration can also increase, okay, when using carbon dioxide. Okay. So, the oxygen is clear, and then hydrogen. So, hydrogen is also known to increase the arc voltage, again because of the convective nature, and known to increase the heat input because hydrogen ionization energy also very high. Okay. So, it is not suitable for ferritic steels for the same reasons what I explained, the hydrogen cracking, coal cracking or hydrogen embrittlement. So, some cases it improves weighting because it also affects the surface tension and viscosity of steels known to change. So, we can also use these to spread the pool effectively for austenitic stainless steels, it is widely used. Okay. So, to summarize, so we can choose the shielding gases based on the material and then how good your geometry should be, the aspect ratio should be, and based on that you can choose, and it will also affect your productivity, because whether you have you want to make a deep penetration welds or the faster welds, or if you want to weld it in a slow without filler, and all these things would be affecting the selection of shielding gas, because the shielding gas characteristics are determined by the heat transfer characteristics we were looking at it, and then the ionization, the arc heat generation characteristics. Okay. So, we look at this table in next class and then we will wind up here. Okay. Thank you.